Hello and welcome to our channel. In this example, we will be using PPC Column Software to design the column shown. The column is a typical column in a parking structure that is carrying spandrels as shown. The design is based on the ACI 318-11 code. The total height of the column is 39 feet. The column is carrying spandrels that are supported by corbels. Each of the corbels is supporting spandrels from both sides. Each of the spandrels is subjected to torsion that produces a force couple F as shown. The typical reactions of each of the spandrels are given. It is required to account for the live load reduction, and the corresponding tributary area of each of the live load reactions are given. In addition to the floor loads, the column will be resisting an earth pressure load as shown. Let's now use PPC Column to solve the example. Using the Define menu, we can define the job titles that include column ID, job title, job number, company name, and engineer name. This step is optional, but this info will appear on the text report. Using the Define menu, we will select the design code. We are using the imperial units here. Next, we define the concrete properties. We will input 7,000 pounds per square inch for the concrete strength. The default aggregate size is 3/4 inch. We will leave it as is. We will select the PCA stress strain model for the concrete compression. Using the Define menu, we can select the steel grade. We are using grade 60 steel. Using the Problem Info window, we will define the main problem data. First, the column height. It is 39 feet in our problem. Then, the column location. The column slenderness effect will be included. We will leave the analysis options without change. Next, we will use the section editor to define the column cross-section data. First, we define the cross-section dimensions. Note that the cross-section sketch will change immediately after any change in cross-section data is made. Then, the column reinforcement is selected. We will try number 6 for all the rebar. We should keep an eye on the reinforcement ratio here to make sure that we are not violating the code. We will now select a tie spacing. Let's try a 16-inch spacing. As you can see, the code requirement status shows unacceptable. This means that we have to select less tie spacing. 12 inches seems fine. Once the column section is defined, the main window will show a view of the column reinforcement. After defining the column cross-section data, let's define the corbels of the column. For each corbel, we shall set a corbel ID and input the geometric information of the corbel. This includes the elevation, depth, span, width, and plan offset. This is repeated for each of the corbels of the column. Note here that it is faster to pick a previously defined corbel and change some of its data and use it to define a new one instead of trying to input all the data again. After adding the Corbel data, you will notice that the main column view is updated to reflect the new added Corbels. Next, we will define the column base condition and the diaphragm locations. First, we change the column base condition from the default fixed condition to the hinged one. Second, we locate the diaphragm elevations. After adding all the diaphragm data, you will notice that the main column view will show the diaphragm locations. Next, we shall define the erection sequence. In our case, we will select the automatic option, which is actually the most common one. Choosing this option means that the column will be braced at the floor level before any load from that floor is applied. We ended up here with 3 erection stages including the final one. Next, we will define the load cases. In addition to the dead load, we have the floor live load and the earth pressure load. For the live load, it is essential here to introduce as many load cases as possible that each can possibly takes place exclusively so that the program can accurately define the envelope straining actions. For example, user shall introduce a live load case for each floor. Moreover, the live load affecting one side of the column at a particular floor level should be included in a separate load case. In our problem, we will set 6 live load cases. Each live load case represents the live load acting at a particular floor from one side of the column. In addition to the live load cases, we will introduce an earth pressure load case. Next, we will verify the load factors. In our problem, we will just use the default code load factors. Now, everything is ready to define the loads. For the self-weight of the column, we shall let the program automatically define the own weight of the column. Using the Corbel loads window, we will define the loads acting on each of the Corbels considering the load cases and the erection stages previously defined. Again here, try to use a previously added data line to add a new one instead of typing all the data again. You can do that by clicking on that line. You can use the main column view to verify that the loads are correctly defined. Everything looks good so far. Repeat this for the rest of the Corbels. Note here that load on Corbel B will be applied on stage 2, which is based on the construction sequence defined. Using the main column view, we can verify that the dead load sequence is correct by checking the dead load applied at each stage. As you can see, this sequence here seems fine. Let's now apply the live loads. Note here that we applied the live load acting at each side of the column in a separate live load case as mentioned before. For the live load cases, you will need to define the live load tributary area in order for the program to estimate the live load reduction. Repeat this for the rest of the corbels. After all the Corbel loads are applied, let's now define the earth pressure load using the earth pressure window. We shall define the earth pressure load parameters as well as the geometry information. Use the main column view to verify the earth load. After we input all the required data, the problem is now ready to run the analysis. Once we click the Run button, the analysis will start. Please note that the analysis might take few minutes to be done depending on the complexity of the problem and the accuracy required. We can monitor the analysis progress using the progress bar in the status box. The analysis is now complete. We can check the straining action diagrams of the column using the straining action menu. We can browse through different load stages. We can also browse through the column sections using the track bar as shown. And we can browse through different load cases including the straining action envelope. We can also view the reactions on the column using the main column view window. Use the combo boxes to browse through different load cases and stages. As you can see, both the reactions on the column base, as well as the reactions at the diaphragm points are given. Let's now see if the column section is adequate or not by checking the demand/capacity window. We shall notice that the demand is shown in a red line, while the capacity is shown in a green one. It is obvious that the demand did not exceed the capacity at any of the column sections, which indicates that the column is safe. The corresponding interaction diagram will be displayed. Using the Corbel design window, we can view or modify the Corbel design. For example, we can modify the tie rebar size to have less number of ties. After closing this window, you shall notice that the Corbel reinforcement will be displayed. We can view a full text report of the problem by clicking on the report icon. The report contains a summary of all the input and the output data of the problem. We can print a copy of the report if we need. We can view a full view of the reinforcement of the column and its corbels. Thank you for watching this video. Please check the information below for how to request a free trial copy of the software.